Hello everyone. In this short video, we are going to talk about the central limit theorem, or CLT, which is an interesting thing in probabilities. And this is also very important for engineering as well. So, what is this? Let me explain it, and then I say why it might be related to engineering or other applications. It says, let's say, for instance, you are an engineer, a test engineer. You are measuring the data from a pressure sensor, okay? And this sensor is noisy. So the readings that you will get are not going to be perfect. They have noise. And because of this noise that has some randomness to it, the distribution of your data, of your measurements, might or might not be a normal distribution. Not all the times the data that you get are necessarily normally distributed. For instance, they could be an exponential distribution or any other types of distribution. Okay? Yep. Now, what would you do as an engineer if you want to get reliable measurements? What would you do? Would you just get one simple measurement and then move on for another set of basically operation condition? You make another measurement? Or no, for the same operating condition you make several measurements and then you report like the average of those, correct? Or the median of them. But here we just want to focus on average. So many times we engineers, we go ahead and make repeated measurements from the sensor, the machine, anything that we are using, and we typically look at the average of that, right? And it could be anything. It could be a voltmeter, it could be, I don't know, a pressure sensor or anything. So that's very common to get samples for the same operating condition and report the average, right? Now, what does that do to the distribution? Remember that each one of those individual readings that you had with the randomness was not necessarily a normal distribution. Okay? Yes? But now that you're repeating the experiments and you're looking at the average of the values, what happens to these averages? Central limit theorem says that if you take many independent samples of size n from any distribution, with a finite mean of mu and a finite variance of sigma squared, then if you look at the average of those samples or mean of the samples, if you plot the mean of samples or get the distribution of those means of samples, guess what? The means of the samples will be approximately a normal distribution now. Remember, individual measurements could be exponential or any other measurements, but now that you're reporting or finding the distribution of the averages of those samples, guess what? These averages are now going to follow a normal distribution, even though the original one is not normal. The average of these samples is also going to be the same as the finite mean of those measurements, but the standard deviation of these averages is going to be the standard deviation of the original ones divided by the square root of n. That is the interesting part. So what happens? I can go from individual exponential measurements to now a normal distribution for the averages. Not only the average of the samples, averages or sample means, is going to stay the same, but the better thing is the standard deviation goes down because n is bigger than 1, so standard deviation is divided by a number bigger than 1, so it drops. So what happens when you're reporting these averages? Because the standard deviation drops, so you go from, let's say, if you do it for more measurements, you go from this kind of distribution now to maybe this kind of distribution. And what does that mean? When you have a smaller, basically standard deviation or a smaller spread of the data, you are way more confident in your number compared to when it's all over the place. So your measurements become more reliable when you take several of them and you report the average. You get more reliable information. That is the most important thing. Why do we do that? Because our information, our measurement end up being more reliable. Not only that, these measurements are now going to be a normal distribution as opposed to the original ones, which could be any type of distribution. And this is the central limit theorem, which is really interesting. Another way to express this central limit theorem is this. It says, assume that you have n independent and identically distributed random variables x1 to xn. First of all, they are independent from each other, which means that the probability of any of them does not depend on the other one. So for instance, p of like x1 given x2 is the same as p of x1, right? Or you can say that p of x1 joint x2 is the product of the two, okay? This is how you define independence. So none of them affect the other one. They are independent from each other, but more importantly, all of them are coming from the same distribution. They are identically distributed. So let's say they are all exponential or they are all something else. And you can expect that for a single sensor, because for a single sensor, really, whatever this distribution of the individuals is, exponential, whatever it is, guess what? It is going to stay the same because that's the same sensor. You have not changed anything. Okay? It says that if all of these independent variables are coming from identically distributed random variables and independent IIDs, and they all have mean of mu and finite variance of sigma squared, then if you form this variable, average of the samples, minus mu, divided by sigma over square root n, as n gets bigger and bigger, as the number of samples in your measurements gets bigger and bigger, you are reporting the average of bigger samples. This variable is gonna converge to a normal distribution with average of 0 and standard deviation of 1. That means, because this is 0, that means mu, the average of this, is gonna be the same as mu, which is exactly what we said, this line. And then the standard deviation of that is going to converge to the denominator, sigma over square root n, which is this one. So do you see the beauty of that? That the averages of these samples will go to a normal distribution with average mu and a standard deviation of sigma over square root n. Or if you normalize it this way, then it goes to a standard normal distribution, 0 and 1. That's another way to express it mathematically. Okay, so first, let me show you that with an application that I made in MATLAB. Let me demonstrate that for you, because you might not believe it necessarily. Let me show you that. And then we are going to talk about another scenario. So first thing first, let's look at the application. So this is the code, and it's written as a graphical user interface, a GUI. Here, there are 5 different initial distributions that you can pick your measurement to be from: a uniform distribution, exponential, chi-squared, binomial, or gamma. Okay? And you have 2 parameters to change, n and max n. What are these? This n here is the number of times that you repeat each experiment. That's the number of trials. The small n, which here you pick maximum of it, here is because as you'll see, this is going to be an animation. So what does this one do? What this one does is it forms these averages for a specific n and plots it for you. Yes? Then it changes the n to a bigger n and repeat and repeat and repeat. Okay? So when you give it this maximum n, it creates these samples with n's anywhere from, let me look at the code, I guess it's from 2, but let me look at that. So you start from some small n, and then you start going to bigger n's one by one, and you want to see the effect of n. There we go. It's a linear space between 1 and max n with 10 numbers. Okay, so you break down the range between 1 and max of n. In this range, you pick 10 equally spaced numbers, and for n equal to each and every one of those 10 numbers, you form this average distribution, this mean distribution, and you plot it. So the goal is to see what happens when n goes up, because the central limit theorem works when n is big. So initially, when n is small, you don't see much of a normal distribution for these averages. When n gets bigger and bigger, that's where you see it is converging to a normal distribution. So the maximum n that you can use in your simulation, here you can pick that. You can go from 1 to 10, you can go from 1 to 500, 700, or 1 to 1000. We don't really let n go to much bigger, because then you need tons and tons of simulations. But here you see, so instead of infinity, we just go to 1000, and then what? So how many times would you do that? Because in order to create a histogram for this, in order to create a probability distribution for this x of n, you need to repeat the experiment, right? You cannot just do one experiment. If you do that, then you only get 1 point, right? Because what you create, for instance, n random data from a normal distribution, or any distribution, chi-squared, not normal, let's say chi-squared or exponential or something. You draw n numbers from basically an exponential distribution. You take their average, and there we go. You get a single number. With a single number, there is no way you can draw a histogram or anything. So you have to repeat that again for the same n, for the exact same n. You repeat it again. You generate n random numbers from exponential, take their average, and this time it would be a little bit different. Then you repeat with the same n, and finally you get what? You can create a histogram. Okay? So you have to repeat this experiment a bunch of times in order to get the histogram. How many times in this application? That is capital N. So capital N is the number of data that you use, the number of experiment that you use for histogram. And you don't want this number to be small, because otherwise your histogram is going to be very rough, okay? You don't have enough data. If you want to form a probability distribution function or approximate it by histogram, you need a bunch of points. So never make this number very small, but don't make it super large. Otherwise, you have to wait for this to do its job. So it is going to be quite time consuming. So right now, I go from exponential initial measurements, and let's say my maximum n is just 10. I do it 1,000 times, and I say animate. Here, it shows the original distribution, and here it is going to show the distribution of the averages. Let's take a look. You see here, the number of samples is changing. And originally, if you saw, the distribution was just like this. It was an exponential. But look what happened. This is just for 10 samples. Each time you grab 10 samples from an exponential, report their average, and repeat that experiment for 1,000 times. Guess what kind of distribution you will get? Almost a bell shape. You see? It's not the perfect bell shape, but relatively good. Let's do it again. You see, initially it was an exponential for n of 1. Of course, for n of 1, you're not taking average, you're directly showing the number itself. But when n gets bigger, now you're doing averaging really, and you see that it's moving away from the exponential and getting closer to a normal. You see here, look at the left one. You see that? Now, if I make the number of data in each sample bigger, this curve that is not like a perfect bell curve is going to get better and better, matching this bell curve better and better, because now my n is now going to be like 100 instead of 10 maximum. Look. $140. You see now, look at this one. This is much closer to a normal one compared to last time. This is a much closer similarity, or much higher similarity to a normal than last one when n was just 10. Here at 141, you are a lot closer. Now let's go to like 500. Of course, you have to wait more. But guess what? At 500, you should be even better. There we go. Now you go to 1000 or something like that. And you see, in all cases, it is converging to a normal distribution, and these deviations are kind of further trimmed. Now you might say, does it really look like one? Well, it's quite a bit better. And if you want, guess what? You can always change that, or you can always change the number of experiments. Like, for instance, if I just do 10,000 experiments each time, then this is going to be a finer histogram. Look. So your data should be more meaningful. Look, you see? Look how close it is to a normal distribution. One more time. Almost perfect. You started completely with an exponential and you ended up with a normal because you are reporting the averages. Now let me go back to 1000, but I changed my initial distribution to a uniform. If I start with uniform and repeat the experiment and report the averages, would I end up with Gaussian again? Look. Here we go. Look. This is your initial distribution. These are the distribution of the averages. Let's go for another one. Like what? Chi-square. Look. Okay, now that we have seen this, let's go back here. I want to talk about one extra thing which is really important. So here we only measured one sensor. We made sure that in that sensor we are not reporting a single measurement each time. We are taking a sample and reporting the average. And the more data we have in each sample, the further the convergence is going to be, and the further these averages are going to look like a normal distribution, and the further their variance would be reduced. So I get more confident in my measurements. They are going to be more reliable. Now, in some places in engineering, in real world, you have several random factors contributing to the randomness of your measurements. So the noise that you get in your system, or the variation that you will get, is not the result of one single distribution, is the result of several of them, which could be added together, contributing basically you're seeing the superposition of them. But the thing is, although these variables are independent from each other, they are from different distributions. So one source of variability is coming from an exponential distribution, the other one is coming from a chi-square distribution or a uniform distribution. What happens under that case? Because here we assume that they are all identically distributed. What if they are independent but not identically distributed? And the variability is the sum of all of these variations. Would you still see a normal behavior in the variable? The answer is it depends. Well, what does it mean it depends? So if you add random variables from different distributions that are still independent, the sum still might approximately follow a normal distribution, but under certain conditions. It's not always going to happen, but under certain conditions it can. What kind of condition? The condition is called the Lindeberg condition, and it is coming from this Lindeberg-Feller central limit theorem, which is a generalization of the classic one I just talked about. This is like a more generalized version of central limit theorem where you relax this assumption that they should be identically distributed. You say, well, they're independent but not identically distributed. Can I still come up with some condition that they converge to a normal distribution? The answer is yes, that condition is called the Lindeberg condition. Okay? And if this condition is satisfied, then the sum still could converge to a normal distribution. Now, what is this Lindeberg condition here? Now, I looked at it mathematically, and it's quite a bit difficult to explain here. It's a very complicated mathematical condition. So what I tried to do is to put it in plain English, something that we can understand instead of me showing you a big formula here. I just want to say what is the essence of this condition. The essence is this, which is very easy to understand. It says none of these individual variables or a group of them should dominate the total variance of this summation. So if x is sum of all of this, then the variance in x should not be mostly because of the variance in x1 or mostly x2 or some of them. They should all kind of have similar contributions to the variance. None of them should dominate the other ones. Now, how does one dominate the other ones? That's when one of them has a sigma much bigger than the other ones. And when does that happen? Well, the distribution that that variable comes from has either heavy tails or it has extreme outliers, and they're kind of the same thing. Because if you have heavy tails, then you can end up with more or less, you can depend on your sigma, you can come up with less outliers basically, or more depending on how you define it. But if you have extreme outliers or heavy tails, then sigma of x1 could be much, much bigger than the sigma of all other xi's. And under that condition, the summation will not converge to a normal distribution. But if they are all kind of similar in terms of their variance, then the summation can converge. And in reality, there are lots of things like that, like human height, like IQ, and so many other things. I mean, if you look at your IQ, it's not just a simple factor. Hey, the only thing for IQ was the IQ of mom or IQ of dad. There is a lot more than that, okay, than ones that we know. Or if you look at the height of human or anything like that, or in some circuits, in measurements, in engineering, there could be a bunch of different factors for noise. I mean, we know only some of them, like electromagnetics, like heat, like light, and other kind of interferences, but it could be several of them. And if they are all kind of playing similar roles, guess what? You still can see a normal distribution for that overall thing. And that's why normal distribution is so common in nature and engineering, is because of the central limit theorem. I mean, not because of it. That's how we described it. That's how we found that in nature this thing happens, and there is a lot of proof behind them. So yeah, I just show it to you as a simple thing here, but there is a lot of proof behind why this is happening. Or deriving this Lindeberg condition, which I mentioned it in simple English, is quite a bit hard, and I don't want to go over to the depth of that. I might not even be a good fit to do that. So, anyways, hopefully you understood a little bit about central limit theorem, and you are going to access now. I limit this to 4. I guess it's enough. And again, you can play with the number of trials, the maximum n. You can look at the animation and how the system behaves. I'll give you a download link under video description for this application. So hopefully it was useful to you. I'll see you in the next video. Thank you.